All right. So for the final lecture of the day, back to ADS-CFT from the swampland. Just some recap of sort of the big statement of ADS-CFT, which we talked about last time. The ADS-CFT dictionary is the statement that relates fields on the gravity side to gauge invariant operators on the field theory side. And at least at large N and large coupling, we can sort of precisely state what we mean by ADS-CFT. It's an equality between a gravity object and a field theory object. The gravity object in this limit reduces to just e to the I times the classical gravitational action, depends on all the fields, and because ADS space is special in its way, we have to impose some boundary conditions at the boundary, and the boundary conditions are that here's the boundary expansion of a field. One of these two independent modes on the boundary will be constrained to be something that we picked, J of x and t. And given that, that's equal to a field theory, a CFT calculation. Basically, what we've done is turn on a source for the associated operator O, and this very same function, J of x and t, is that source. So this is sort of the big picture here. We talked about how there's variations you can do on this. You can have the alternate quantization instead of the regular quantization, where you constrain beta instead of alpha. But sort of the principle is the same. Boundary conditions that you fix on fields on the gravity side are sources that you turn on for the corresponding operators on the field theory side. So this is all for scalars, and we talked in some detail about how you have to regularize the classical action, you have to add some boundary terms, you have to make sure that things look regular when you take the regulator away. I'm not going to go into really any detail at all for other fields, but I'll just sort of mention that they exist, and you can do something similar. And in particular, there are two other sort of bosonic fields that are famous and we need to talk about, which is the metric and the gauge field. And so for other bosons, bosons will have a second-order differential equation, just like the Klein-Gordon equation for the scalar. And so they'll also have two different independent modes on the boundary. And so we'll do a similar thing where one of them, so the two modes on the boundary, and we'll end up with one of them is the source, and one is the expectation value, which is what we found for the scalar. So the same sort of thing holds in that case. And actually something similar holds for fermions. The story just looks a little different because they have first-order differential equations, but they make up for it by having extra components. But so the two that we want to mention, we have gravity, so we always have a metric. So we ought to have something on the field theory side that we also always have, and that something is the energy momentum tensor. And so the behavior of the metric near the boundary, which I won't write down in any detail, contains the expectation value of the energy momentum tensor, but also the source for the energy momentum tensor. The source for the energy momentum tensor looks like a four-dimensional metric. That's sort of the definition of the energy momentum tensor, or one definition of it, is that it's the thing that you get by varying the metric. So that sort of works in this correspondence that the appropriate components of the higher dimensional metric become the source for the energy momentum tensor in the field theory. So that's one of the bosonic fields that I wanted to mention. And then the other is we talked about how if we have gauge symmetries on the gravity side, that corresponds to global symmetries on the field theory side. So if I have a gauge field, A mu, on the gravity side, there must be some conserved current that this is associated to. And in fact, the dual operator is just J mu, which is the conserved current, associated to whatever that particular symmetry, global symmetry on the field theory side is. And again, this sort of correspondence makes sense. Certain modes near the boundary of this gauge field will be the source for the conserved current. And when we write down a source for a conserved current, that's something we think of as maybe an external, a background gauge field. So again, it makes sense that sort of these would correspond to each other. So having mentioned these, I can talk a little bit about a way to introduce thermodynamics into the gauge gravity correspondence. This was mentioned by Johanna in week 1 also, so I won't mention it in huge detail, but I will mention it. And for the applications I have in mind, the metric and a gauge field will be the fields that I need to sort of realize this. So let's imagine that we have a planar geometry, planar horizon for black hole. And I'll write some general form for the metric. There's some function of the radial coordinate times the Minkowski metric, and then some other function of the radial coordinate times the radial coordinate itself. You can play with reparameterizations of R and change that, but let's just sort of leave that general. And if there is a black hole horizon, we'll say that RH is the largest value of the radial coordinate where we have a horizon, which is realized by a 0 of the function that I didn't write in there. Good job. OK, so there should be h of r here times dt squared plus dx squared. OK, so I've broken manifest Lorentz invariance in the lower dimensional theory by turning on this particular horizon function that multiplies time squared only. And the 0 of that is where I have the horizon. From that, you can calculate what the temperature is of the associated black hole. And Johanna went through this calculation. There are many ways you can do it. Sort of maybe the most fundamental way is to actually go through and calculate how the Hawking radiation works by doing some Bogoliubov transformation. In practice, nobody does that. What people do in practice is to continue to Euclidean space near the horizon, and they get a geometry that will have some deficit angle and be singular unless the periodicity of the analytically continued time coordinate takes a particular value. And that gives you the temperature. So I'll just write down that it's e to the a at the horizon minus b at the horizon over 4 pi times the derivative of this vanishing horizon function. So the important conceptual thing here is that we have a black hole now on the gravity side, and it has a Hawking temperature. And that is the temperature of the state of the dual theory. That's sort of a natural thing that you might think the temperature would be, and that's what it is. You can talk about the Hawking temperature is measured at infinity, though my formula here is in terms of this metric at the horizon. Yeah. Yeah. Oh, yes. Let's see. The way I will do this is the one I just wrote will go up, and the earlier one will go down. Thank you. Another thermodynamic quantity that we can think about is the entropy. Our black holes here are planar. They have a planar horizon. So it's actually, there'll always be a factor of the volume there. So it's the entropy density that I'm really going to be interested in. So little s. And this is 1 over 4g times the area of the event horizon. So I'll integrate over the d-dimensional metric at a constant r, the constant r being the value of the horizon, r equals rh, and I'll get an overall factor of the volume in lower dimensions, which I'll divide out by. And if you go ahead and calculate this, it just gives you a factor of this a, so e to the d minus 1 times a evaluated at the horizon. So the entropy density is just the related to the area of the black hole horizon. So that's 2 of the thermodynamic quantities I'm going to be interested in. The other 2 are I may have a conserved current, and that conserved current, I can turn on a chemical potential for it, as well as have a density for it. Yeah, question?
Why is this not the walled entropy?
Why is this not the walled entropy?
Why aren't you evaluating the integral Wald tells you to evaluate for black hole entropy?
I guess I don't know what Wald told me to do.
That's for higher derivative. He's doing Einstein gravity.
Yeah, I don't have higher derivatives. This is just sort of the simple area. Yeah, so if I want to turn on a chemical potential or a density for a particular conserved current, so density rho for a conserved J. Well, what is that? The density is just part of the current. It's the time component. So I'll take the expectation value of the time component of that conserved current. And then if I have a source for J0 turned on in the field theory, ddx times some constant times J0, that source is just the chemical potential. But I can also see that putting this into context of a source for one component of J, that this is A0 on the boundary. So both the chemical potential and the density will end up being part of the gauge field. One of them is the expectation value of one of the components. The other is a source for one of the components. So the time component of the gauge field, as I go out to infinity, has the leading term, which is the chemical potential, and then the subleading term, again, this is the source and VEV dichotomy, which is the density. There's a hidden gauge choice in here. A constant in a gauge field, in principle, is not physically relevant. And so the fact that I'm getting something physical out of this constant, I've implicitly assumed that A0 is equal to 0 on the horizon. And then what's physical is the difference. So, sort of neat and satisfying thing that comes out of ADS-CFT is that finite temperature and density systems are dual to black holes with a gauge field, with an electric field. And so a lot of what people do when they're interested in studying certain states in the field theory is to look at black holes with horizons, with electric fields, and sort of check out their properties, and that tells us about finite temperature and density states. So before I do an example, I just want to sort of orient some big picture concepts of how I tend to think about the kinds of models that we can build for these systems using ADS-CFT, which is the dichotomy between what's called top-down and bottom-up constructions. So let me just make a little chart. So here's a line. This is sort of a new subject. And then top-down versus bottom-up. Two different ways to sort of use ADS-CFT to study field theories. So here's top-down. Here's bottom-up. And they both have their good points and their bad points. So make a little chart here. Here's the good points. And here's the bad points. So it's a balance. The good points of the top-down. OK, so first, what do I mean by top-down? And what do I mean by bottom-up? By top-down, I mean that I'm going to take a known duality that was induced through string theory. Something like ADS5 cross S5 is dual to n equals 4 super Yang-Mills, ABJM theory and M theory, or one of their descendants, or anything else that we sort of have an argument for how it should be from, I don't want to call string theory first principles, but from more guiding principles than none. So that's a top-down construction. And the good thing about top-down is that the dictionary and the dual field theory are really known precisely. If you do a calculation in ADS5 cross S5, you can say this is n equals 4 super Yang-Mills. That's the theory that I'm looking at. And so your whole calculation is on firmer footing. But nobody's perfect. And if you've ever looked at ADS5 cross S5 and its Kaluza-Klein reduction down to n equals 8 gauge supergravity in 5 dimensions, you know that this is complicated. And it's also, because it is what it is, it's a rigid theory, it's fixed, it's less flexible. Maybe we want to look at a certain physical phenomenon, but it just doesn't happen to exist in n equals 4 super Yang-Mills, for example. So what people do sometimes is they pursue bottom-up construction. So what is a bottom-up construction? A bottom-up construction is when I say, I'm going to write down a gravity Lagrangian, and it's exactly what I want it to be. And nobody gave it to me, but I just made it up. There's a metric, and okay, I need a U1 current, so here's a gauge field. And maybe I'll put a scalar in there, because it does something I want, but I made it up. So the good news about that is that this can be as easy or hard as you want it to be. And it's quite flexible. Oh, whoops. Thanks. All right. I have a hard time keeping happiness and sadness straight sometimes. So this is as easy as needed, and it's flexible. But then the downside of this is that you don't even know necessarily what the dual is. You can establish what the symmetries are, but you don't really know, if you just write down some gravity Lagrangian, what that's dual to. The symmetries are there by definition, but besides that, it's just some large N gauge theory. Or it might just not exist. Does it even exist? So I've gone through periods of more and less skepticism of whether certain models that are bottom-up even exist. And that's sort of the contrast to firmer footing here. These are both sort of opposites to the ones that they're diagonally related to. So my ultimate feeling about this is that both are valuable. That bottom-up constructions are nice for getting exactly what you want and seeing if it's even possible in the gauge gravity duality. Top-down is useful for studying theories that we know and love and care about and knowing that it's on a firmer footing. So I'll talk about both of these things.
But even in the top-down case, aren't there cases where basically all we know is that it's the theory defined by that bulk, like the theory on...
In some cases, I suppose. So right. So the question is, even in top-down cases, don't we sort of only know one side? So some cases are better than others. ADS5 cross S5 and n equals 4 super Yang-Mills, we feel like we know pretty well. But you're right. ADS7 cross S4 is dual to this particular 2,0 theory in 6 dimensions, which maybe we know the most about it from ADS-CFT. So, but we can also, I mean, in my career, we learned a lot more about the theory on M2 branes than we used to know. I mean, we now know ABGM theory from 10 years ago, which we didn't know before. So it's possible that the other side of that will get filled out more as well. Okay. So I was going to take a few minutes to talk about a bottom-up model that illustrates some of this sort of thermodynamic construction and relates to one of the big theories that we're talking about, which is QCD. So I'm going to talk a little bit about the QCD phase diagram. Some of this is work that I did, so I like talking about it because it's fun, but I think it's also a nice illustration. So a couple of things about QCD is that as you vary the temperature in QCD, you expect some fundamental things to change. At low temperature, you have confinement, and you also have chiral symmetry breaking. And as the temperature gets higher, we expect that these go away, that the theory deconfines, and that chiral symmetry is restored. Now, moreover, in the real world, chiral symmetry is not exact. There are terms in the standard model that break it. quark masses. And so we don't expect an exact phase transition. So this is not a phase transition, at least not at 0 temperature. It's what's called a crossover. Crossover is something that wishes it was a phase transition, but isn't actually a sharp change. It's just a sort of gradually sudden or suddenly gradual change. So, for example, there's lots of lattice data calculating quantities like how, with temperature, does the entropy density vary? Now, the entropy density actually has units because of the volume in the denominator. Let me calculate a dimensionless thing by normalizing it by t cubed. And so if you calculate this on the lattice, you find that it's pretty low, and then suddenly it gets much bigger, and then it levels off. This is just a qualitative sketch. But the idea here is that at this point, at this crossover, you're seeing the liberation of quark degrees of freedom and gluon degrees of freedom. So if this were large n, then we'd be going from the entropy scaling with n to the 0 here to scaling with n squared here. Well, we're not at large n, we're at n equals 3, but still, we have a lot more degrees of freedom after we get to this point. But it's a crossover, it's not a sharp phase transition. One thing that people have thought about a lot, let's see, this one. I did the wrong order. Sorry, Matt. One thing that people have thought about a lot is extending this into a two-dimensional phase diagram. So baryon number is conserved in QCD. And let's imagine that we turn on a chemical potential for J baryon. What happens? Well, I won't try to explain why people who are not doing ADS-CFT have this expectation. But the expectation is, so here's mu equals 0. Here's where the crossover is. The expectation is that as you get to higher chemical potential, that this crossover gets sharper and sharper and sharper until when you reach a certain point, it turns into a line of first-order phase transitions. So the crossover sharpens. So let me write, this is an expectation. The crossover sharpens into a first-order line, which ends on a critical point. And Silviu Pufu talked a bit about phenomena like this, second-order points at the end of first-order lines, and critical phenomena, and so on. OK, so what can we learn about mu not equal to 0? Well, all this wonderful lattice data at 0 mu is much, much harder to get when you move to non-zero chemical potential for technical reasons. So for mu not equal to 0, it's very hard to get good lattice models of this. The reason is that mu not equal to 0 leads to complex terms in the Euclideanized action. And this makes the Monte Carlo sampling that lattice people do much, much, much more difficult to implement properly. This is called the Sine Problem. I hope I said nothing but true words there. And that if you have any more questions about that, you can corner Professor DeGrand at some point. But this just means that lattice QCD, which works so well without the chemical potential, starts having a lot of trouble with a chemical potential turned on. So that's where ADS-CFT can sort of rear its head here, because ADS-CFT does not care about the Sine problem. So there's an idea that maybe if we could build a holographic model of at least part of the QCD phase diagram, that it would not suffer from any difficulties moving off the t-axis. Well, the crossover in my diagram is on the t-axis. Yeah, the t-axis is mu equals 0. Oh, you mean like how high up? I was sort of imagining that this word sort of spans this. So the crossover is, you know, I can't quibble about factors of 2. It's approximately the same distance up as the critical point on the top end of the first order line. I can't be... But we don't know where the critical point is, which is the only other thing setting the scale. So.
Oh, I see.
Yeah. So yeah, that's the only thing setting my scale. So. Can a crossover become a phase transition at large? Is that? Sorry. So yes. In fact, in some cases, you can only get phase transitions at large n that become crossovers at finite n. Yeah.
This is a crossover because the zero quark mass limit in the second order second order transitions can't survive such things. Number of colors.
All right. So thank you, Tom, for providing more wisdom. And so what is the model that I'm going to build? I'm going to build a bottom-up model of the QCD phase diagram. But I'm going to use the wonderful lattice data that we already have as an input. So here's how it's going to go. I am going to make up a bottom-up Lagrangian. Here's an Einstein term. Here's a scalar field. It's got a potential. And I'll also have a gauge field. And there's some function of the scalar field that multiplies it. What are these fields? Well, the metric is dual to T mu nu, as it always is. It always has to be there. I've introduced the gauge field because I want a model with a chemical potential for baryon number. So let me just put in a gauge field. What about the scalar? Well, if I just have a solution in ADS5, it's conformal. It's dual to a conformal field theory. And QCD is not a conformal field theory. I'd like to do something that implements the non-conformality of QCD. And so QCD has a coupling that runs. It runs slowly at high energies, where it's asymptotically free, and then runs more quickly at lower energies. But I'm going to do the high energy part by adding this scalar, which is dual to some operator. And that operator has a almost marginal, but very slightly relevant conformal dimension. So by allowing this scalar to run, I will be adding a source for something that's an almost marginal operator, and that will sort of play the role for me of the running of the QCD coupling. Meanwhile, I have this function of the scalar and this function of the scalar, and this is a bottom-up model. They could be anything at all. What I'm going to do is I'm going to choose just some function that I like. I'm going to end up with some sums of exponentials, coshs and 1 over coshs. Yeah, question? Why which particular number? Oh, 3.93 as opposed to 3.92? Yeah, it actually comes from the particular potential that I chose, expanded to quadratic order. I want something that's almost marginal, but the exact number is not very important. This whole thing will turn out to be sort of more a statement that something can happen rather than every number is right to the second significant digit. So I can mess with different functions here. And when I do that, I can numerically generate black hole solutions for all sorts of different choices of these functions. So there'll be different theories with different choices of the functions. And I can examine the thermo thermodynamics of the different black holes that I make, and I will match what I get to lattice data for S as a function of t, and also the quark susceptibility, which is just the variation of the density with respect to the chemical potential as a function of t. So this first one was done by Gobser, Nalori, Silviu, and Rocha, and then the second part and the rest of what I say was me and Gobser and Chris Rosen. And once we do that, it's kind of cool. I've got this theory where I just made up some functions of phi, where if I make black holes and look at what kinds of thermodynamics those black holes have, they lie more or less on a curve like this. So by messing with V and F until it looked like something I wanted it to be, I have baked in the crossover to this theory. Okay? And it was totally arbitrary. It's bottom up. I just picked something that made me happy. So up until this, thank you. I just picked something that made me happy. And so far we haven't done anything new. We just said, hey, look, here's some black holes which can look like lattice data. But now we're going to use the fact that in ADS-CFT we can turn on mu and also make a whole family of black holes with a non-zero chemical potential and density. ADS-CFT doesn't care. Unlike the lattice, it's happy to sort of generate these. I mean, the lattice has other virtues like actually doing QCD. This is not actually QCD. This is something whose thermodynamics was built to look like QCD. And so we make all these other black holes now. And we turn on chemical potential and see what we get. And the way we do this in practice is we start at the horizon with some initial conditions, phi at the horizon, the derivative of this at the horizon as initial conditions, and then we just integrate out. So this is a problem in numerical ordinary differential equations, basically. And I can fill out a phase diagram. Each black hole that I get from these initial conditions, I look at its behavior near the boundary. And I say, well, how is A falling off? That gets me mu. That gets me rho. What is the horizon area? That gets me the entropy. I see all these black holes, and I can plot them. And the result is that as you add finite mu, the crossover sharpens into a line of first-order phase transitions. So if I plot at fixed t, so here, for example, is rho as a function of the chemical potential. If the temperature is greater than the critical temperature, then this sort of just goes up. But if I look at a bunch of black holes that I've generated for some t less than the critical temperature, when it gets to a certain mu, it turns back on itself. And this is exactly what you expect when you have a first-order phase transition. If you pick a particular point, then these two here, these are two different black holes. These are the competing phases near the first-order line. There's always a third one in the middle, which is thermodynamically unstable because the derivative of this function goes the wrong way. So we see three different black holes here. So it's really sort of nice to see that when you're numerically calculating black holes in 5 dimensions, and you look at some properties of theirs, they can look just like the thermodynamics of a dual field theory, to the extent that if you start it with a crossover, it knows just what to do. It will happily develop this line of first-order phase transitions. So it's nice that the black holes know enough about thermodynamics to know to do that. And then another question you can naturally ask is, what about the critical point? So there's supposed to be a critical point at the end of the first-order line. And you can calculate the critical exponents looking at these black holes. Silviu talked a little bit about this concept. So people have guessed we think that this QCD critical point is in the universality class of the 3D Ising model, which is the same as the universality class of the water liquid gas transition. So what do we actually see in these ADS-CFT models? Well, it's interesting. It tells you both about how much ADS-CFT knows and how much ADS-CFT doesn't know yet. You get, very obviously, the critical exponents of the three-dimensional Ising model, but it's not the true quantum renormalization group critical exponents. It's what you get if you only do mean field theory. So it's like it's trying to tell you that it's the three-dimensional Ising model, but it can't get the quantum part. It can only get the classical part. And I think it's a real demonstration of limitations of this approach. Even though the field theory is very quantum, on the gravity side, we're working in the classical limit. The large n limit becomes the classical gravity limit. And so it seems that because we're in this classical gravity limit, that we've suppressed all the quantum fluctuations. Yeah, maybe I shouldn't. I was just thinking, maybe I should walk that word back. We have suppressed fluctuations. On the gravity side, we have no quantum fluctuations. And that means that on the field theory side, we are missing the appropriate statistical fluctuations to get these critical exponents. Thank you. So that's what I wanted to say about that. But
can you add them?
What's that?
I mean, can you do some quantum gravity and get corrections? Or?
Yeah, I thought about that. I haven't tried to do it. So certainly a natural thing to try to do is to add quantum corrections on the gravity side, 1 over n corrections, and see if those 1 over n corrections actually get you the actual critical exponents. That would be delightful. I haven't attempted it. Hint, hint. Okay. Any questions at this point? Yeah, Jasmine. So the question was, is there any hope for getting a meaningful result for the location of the critical point? So when we published this paper, we definitely gave a location in MEV, just so if people found it right there, that we could say that we found it. But honestly, there's a lot of ambiguity here. I didn't constrain these functions in my bottom-up Lagrangian to be the best possible functions. We picked some that looked pretty good. And it was more a demonstration that it could work. So if you really wanted to be confident that you were making some sort of prediction about it, you'd have to quantify sort of in the space of functions how close to the best were you doing, and then you'd have to worry about the fact that you're not really doing QCD. So I feel like the existence of the critical point is a nice result, and I'm much less confident about the exact location. Okay. So from talking about thermal a little bit, oh yeah, go ahead. So the question is, how do we calculate the critical exponents of the 3D Ising model from the gravity side?
Yeah, even for the mean field theory.
Even for, well, I have not attempted to calculate the quantum corrections on the gravity side. If it were something I felt like I could do. Well, I'm saying that if I wanted to go beyond mean field and the field theory, I think I would have to go beyond classical physics on the gravity side. I think I'd have to include quantum corrections. Okay. So this was mostly just to illustrate how, these black holes have these particular properties which really can map into real thermodynamic systems in the dual field theory, but with limitations, which maybe we can move beyond. So my next topic is I want to talk a little bit about 2-point functions In principle, we can talk about all sorts of higher point functions, but I'm going to stop at 2. So let's recall that some field, thinking about a scalar field, but you can generalize this, has this expansion near the boundary. So this is at r goes to infinity, alpha over r to 1 power, and then beta over r to the other power. And we talked last time about how for the regular quantization, at least, alpha corresponds to the source for the dual operator, and beta corresponds to the expectation value of the dual operator. So this is the regular quantization. For alternate, you just switch them. So what if I would like to calculate a 2-point function of that operator? Well, to pull down another factor of O, the operator, I need to vary with respect to j again. So being schematic, not attempting to get factors right, this 2-point function is a variation of the 1-point function with respect to the source. And you can set the source to 0 at the end. So it's the variation of beta with respect to alpha. Now, why do beta and alpha have anything to do with each other? So just doing this expansion near the boundary, beta and alpha were the 2 independent solutions. Near the boundary, they have nothing a priori to do with each other. So to calculate a 2-point function, we have to move beyond just looking at things at the boundary. We need to see how these are related. We need, in general, the full solution for phi going into the rest of the bulk. And in fact, in general, we need to impose a boundary condition. So let me not write BC. Let me write boundary condition, or at least boundary cond, at the other end of the geometry, in the infrared. So we can't actually calculate 2-point functions just from sort of looking at limits near the boundary. Not in general, not unless something really special is happening. We need to find the real solution. In general, beta will be equal to some number times alpha plus higher order things. So to leading order, this correlator, OO, instead of just the variation of beta with respect to alpha, is just beta over alpha, with then alpha set to 0 at the end to turn off the source after you do it. So this is just the ratio of the response to the source. And I hope that this sort of has a sort of physical understanding to it. The source is we're kicking the system. We turned on some kick, we did something to it, and it's going to respond in some particular way. The correlation function is, well, I didn't write arguments, you can think of these as x and y. It's if I kick it here and x, how does it respond over there at y? So that's the idea of calculating this 2-point function. If all we're interested in is a 2-point function, then all I have to do is solve the linearized phi equation. I don't need phi squared and higher order terms, because those will drop out. I'm only going to end up needing 1, essentially, to calculate this ratio here. I basically just have to solve for the linearized equation, find these, and take the ratio. If I needed to do higher points, which I won't do, higher point correlators, I'll need higher powers of interaction. So in pure ADS, which I won't do this, but in pure ADS, you can solve the Klein-Gordon equation. The Klein-Gordon equation solutions can be written in terms of Bessel functions. And you can actually relate the alpha to the beta. And in general, the boundary condition here is that it be regular, not singular. In the deep infrared, far away from the boundary. You take the non-diverging solution. And this reproduces the known CFT form for a two-point function, which is that this look like some constant over x minus x prime to the 2 delta. And in the early days of ADS-CFT, there was a whole industry of calculating 3-point functions and 4-point functions, and all of the things that you can say about CFTs are reproduced exactly by analogous things that you could say in the gravity side. I guess I still have one I can erase over here. So for the last, half hour of today, and for my final lecture on Friday, I'll talk about a bunch of different kinds of geometries and some of the different physics that we can study in the dual field theory from looking at those. I started by telling you about temperature and density and looking at these QCD phase diagram black holes. I'll bring temperature and density back in a second, but first I want to talk about a kind of solution that doesn't have any temperature, no black hole horizon, no finite density, but we do something else instead, which is to turn on a scalar field. And these are so-called renormalization group flow geometries. So renormalization group, or RG, flow geometries. And I'm just going to give a couple of examples of how actually sort of similar looking things on the gravity side can lead to quite different physics on the field theory side. I'm trying to remember to put this up. Okay, so the idea here is that I'm going to consider a metric where I keep four-dimensional, or whatever the CFT dimension is, lower dimensional Poincare invariance. So I've still got eta ij, dxi, dxj, but I'm no longer requiring myself to be anti-de Sitter space everywhere. And the reason that I'm not an anti-de Sitter space anywhere is I've turned on a new field. I've turned on some scalar to vary with R. So the fact that things are varying with R in an un-ADS way, like now, is that a sentence? The way things are varying with R, taking it away from anti-de Sitter space, implies that we're breaking scale invariance. Because our symmetry that translated us in the radial direction is going to be broken by this. I'm still going to assume that this goes to ADS d plus 1 at the boundary. So I'm not changing the boundary where I fix my boundary conditions, but things are going to start to deviate as I move away from that. And the nature of how we're going to break scale invariance is going to be visible in this scalar. So I'm going to give 2 or 3 examples of different geometries that sort of have different physics to them. I'm going to do this all in a context. Oh, let me write before I do that. I know I said it, but this preserves d-dimensional Poincare invariance. So I'm going to choose a particular context to do this in, and my context is going to be n equals 8 5-dimensional gauged supergravity. Now, I will write my table on another board. I'll write my basic stuff here. So n equals 8 5-dimensional gauged supergravity. Sounds kind of Baroque, but it's what you get when you keep just the lowest Kaluza-Klein modes from reducing the 2B on ADS5 cross S5 solution. So you're integrating out, maybe integrating out is a bad word, but you're doing the Kaluza-Klein expansion on the S5, keeping the tower of modes that you get in ADS5 just to lowest order. There's a symmetry here, SO6, which is the isometry group of the S5. And then it turns out when you do this, there's a whole bunch of scalars. And there's 3 particular kinds of scalars that appear. And I'll just sort of mention them. So here's a table. First of all, what type 2b supergravity fields did these scalars come from? What are their SO6 transformation properties? What is their mass in anti-de Sitter space? What is the dual conformal dimension corresponding to that? And what is the n equals 4 operator that they're dual to? So there are some scalars that come from taking the metric and the 5-form field strength. These are both turned on in the background, so fluctuations of them couple also. These sit in a certain 20-dimensional representation, because 20 was already taken and 20 bar was already taken. This is called 20 prime. They have m squared L squared equals -4. They actually are at the Brighton-Lohner-Friedman bound in 5 dimensions. They correspond to dimension 2 operators, which are just quadratic in the scalars. Trace xi, xj. Another set of fields come from the 3-form field strengths, H3 and F3 of type 2b. These end up in the 10, which is complex, and its complex conjugate of the SO6 group. They also have negative mass squared, but it's not all the way down at the Brighton-Lohner-Friedman bound. They have dimension 3, and these correspond to fermion bilinears in n equals 4 super Yang-Mills. Finally, there's a 10-dimensional dilaton. Really, there's a complex field which comes from the 10-dimensional dilaton and the axion. So this is 2 singlets under SO6. It is massless. It corresponds to dimension 4. And the dual operator is trace f squared plus a lot more stuff. And actually, by the time you get done with the lot more stuff, it's the whole Lagrangian of n equals 4. So I'm just going to mention a couple examples of looking at different geometries with these scalars turned on in the background and what that tells us about the dual physics.
So there's other fields you just are not turning them on or whatever.
Right, that's right. So I listed all the scalars. There are certainly other fields of the supergravity theory. That's just the spin 0 ones. There are also other modes higher up in the Kaluza-Klein towers, which I'm not talking about. And I'm going to choose to just turn on one scalar at a time.
But that's all the scalars of the 5D theory?
That is all the scalars of the 5D theory. 42, right? Yeah. Okay. So some examples of renormalization group flows. What is that? Well, it's a solution of that form that I wrote over there to the Einstein-Dilaton, or Einstein-Klein-Gordon, maybe I'll just say, coupled set of equations that approach anti-de Sitter space. So the first one I'll mention, I'll call the Coulomb branch flow. And so what is that? I took a scalar, which was in the 20 prime. So it has delta equals 2, and the operator is a quadratic in the n equals 4 scalars. This solution, it turns out, is supersymmetric. It preserves half of the supersymmetry, 16 supercharges. So Kumran was talking about how it's often nicer to think about just pure numbers of supercharges instead of how big your n is, because numbers of supercharges don't change when you compactify on tori. So I'll just say it's half maximal supersymmetry. And the solution for the scalar, in principle, has a leading log r over r term. This log shows up in these Brighton-Lohner-Friedman bound scalars. But in practice, the coefficient here is 0. But there's a non-zero subleading piece for a parameter L. So for this particular geometry, there's 0 source, but there's an expectation value of the scalar, which is L squared. So the interpretation for this is that we have turned on a vacuum expectation value for x, but because there's no source, we haven't changed the theory. The theory is undeformed. It's still n equals 4. So scale transformations are just spontaneously broken. The geometry is singular in the infrared. There's no black hole there, remember. Haven't turned on a temperature. It's singular, and that might worry you. But actually, people were able to show that this lifts to a 10-dimensional solution, which is just what you would get from a disk of D3 branes, spread out, not all sitting in one place. So the original motivation for ADS-CFT involved a bunch of D3 branes sitting on top of each other, naturally generalized to being on the Coulomb branch of the theory where you move them away from each other, and that corresponds to turning on some VEVs. So the fact that it's singular shouldn't really bother us, because it just looks singular in 5 dimensions. In 10 dimensions, it's fine. And you can calculate a 2-point function. Well, instead of calling it phi, let me call it OO. You can calculate 2-point functions, both of the scalar that's turned on or other things, and you find hypergeometric solutions. But the interesting thing is that there are singularities telling you about the spectrum. The spectrum is that there's a gap to p equals little l over big L squared, and then a continuum above that. So this is also consistent with our expectation that turning on this scalar on the gravity side just means that we've given an expectation value to some fields in the field theory. All we've done is sort of introduce a gap up to the location of that VEV, and then we have our usual continuous spectrum above that. So I want to contrast this with something that looks very similar as far as the gravity side is concerned, which I'll call the n equals 1 flow. So now let me pick my scalar. I'm not going to try to use a different notation, just still call it phi, but now it's in the 10. So looking at that table over there, that's a scalar with dual to an operator with conformal dimension 3, which is trace fermion squared. And this solution involves, so there's a 1 over r term and a 1 over r cubed term. And I'm not too interested in the subleading term. What I'm interested in here is that there's a leading term here with some constant that I've called m. And so by adding this is a source for the operators trace lambda squared. And so by introducing this, we've actually deformed the theory. It's not n equals 4 anymore. We made it into something else. This is what Dan Harlow didn't want to do in week 1, because he wanted to stick with his one theory, but we're going to change it. And I guess I didn't mention that this breaks n equals 4, but it preserves some supersymmetry to n equals 1. It seems like by turning on a source for this, we've turned on a source for a bunch of masses for fermions. How can we be preserving supersymmetry if we're turning on masses for fermions only? So the statement is that this actually corresponds to masses for the 3 chiral superfields in the n equals 1 decomposition of n equals 4. So where are the bosonic masses? I see the fermionic masses, but where are the bosonic ones? Well, what they would look like, the bosonic mass operator would be trace xi, xi, which is not one of the operators in my table. My table I had xi, xj, with I and j different, the symmetric traceless combination. This is the trace. And this operator actually doesn't appear on the gravity side, because this operator is not protected, and this has high dimension. And so the idea is that it's turned on, but we just can't see it. We might not even know that it was turned on, except supersymmetry is preserved, so it must be there to go along with this. That is the Kanishi operator, yes. So instead of just deforming n equals 4 to a different state, we've turned it into a new theory. And what happens when we do this, so if we calculate some correlators here, we also get hypergeometrics, but they look quite different. Now instead of having a gap and then a continuous spectrum, we find discrete poles at certain p squared, some constants times n squared for some integer n. So the interpretation of this is now instead of a continuous spectrum, we have this discrete spectrum of very particular states. And so these are sort of the supersymmetric analog of glue balls. So if you just stared at these two, sorry, I can't pull this down at the moment. If you just stared at these two different geometries on the gravity side, they look very, very similar at first glance. But when you look carefully at the behavior of the scalar at infinity, you learn that the scalar is very different in the two cases. In one case there's a source, in the other case there isn't. Two totally different things in the dual field theory. And that's reflected in the fact that in one case we still have spontaneously broken conformal symmetry, and we still have a continuous spectrum above a gap. But here we have explicitly broken conformal symmetry, and we have these discrete glue ball states.
What does this one look like in the IR?
It's also singular. And it's also singular.
So the glue balls are like KK modes in the IR or something?
Well, the glue balls are, oh, I see what you're saying. Yeah, so for one given field, the given solution for the two-point function has many different poles. And I guess you're asking me, and I don't know the answer, if I went to the near IR solution, would I see them each as sort of a separate mode there? That's a good question. Yeah, I don't know. That would be, yeah, I don't know. Okay, so these are just two different examples of these flows. There's a third kind, which I'm not going to talk about in any detail. In fact, I will mention it just to say the one interesting thing about it is that you can also have a flow from ADS to a different ADS, where here phi is equal to 0, but here phi is equal to some phi star. So you're at a different critical point of the potential. And this corresponds to a flow from a CFT in the UV to a CFT in the infrared. So instead of having a singularity in the infrared, this kind of geometry picks up another ADS region with a different ADS radius corresponding to a different conformal field theory. I had maybe 3 things to say about that, but I think that's all I'm going to say, because I have about 10 minutes left. I want to start talking about the quark-gluon plasma. Sorry, say again? That has a source as well. Yeah, it has a source. Yeah, because here we're really changing the theory. So the infrared CFT is a new theory, and we basically what we're doing here is the source we turn on is a relevant operator that perturbs the UV CFT, and then it flows to an IR CFT. And you can see, in general, I need two scalars to do this, and if I don't tune the coefficients just right, I'll get a solution that misses the critical point and just sort of goes off to some singularity. So we interpret that as a solution that doesn't actually find this IR CFT in the renormalization group flow. Right, so yes. So when singularities in the infrared, I don't know if I'm ready to make this a 100% all the time statement, but yeah, they're associated with some sort of gapped behavior in the spectrum. Different dimension of ADS. So, I mean, it's still a D+1 dimensional geometry. There are interesting examples, which I might talk about next time, where in the infrared you have a smaller dimensional ADS cross some other factor. So that can happen, and then you effectively have a sort of smaller dimensional CFT. But the overall geometry preserves dimension. Okay, so let's talk. In the few minutes we have left, let's just set up what we'll talk about at the beginning of next time, which is QCD and the quark-gluon plasma. So we've already talked about QCD and this crossover, and how the entropy gets really big at the crossover temperature. And this is associated with the fact that we know that at 0 temperature, and at low temperature, the states of QCD are hadrons. But at high temperature, we expect that crossover to take us to liberated quarks and gluons. The theory is asymptotically free at high energies. High temperature should mean that we're sampling high energies more and more, and so we expect to see liberated quarks and gluons. This is due to asymptotic freedom. So people were getting ready to study the state of QCD at high temperature that you could generate in heavy ion collisions. So heavy ion collisions going on for some time, but between 10 and 15 years ago, experiments at the relativistic heavy ion collider started up, which explored, by colliding these heavy ions, they created for a brief moment hadronic matter, or maybe I should say QCD matter, with a high temperature. And then later, when the LHC came online, the LHC is also doing heavy ion collisions now. So this explores QCD matter at high temperature. And the idea was to try to probe this crossover and to try to see this state of liberated quarks and gluons. And there was a name for what this liberated state of quarks and gluons would be before it was even seen, which is called the quark-gluon plasma. But what was interesting, very interesting, is that when people got the results back, they didn't actually see mostly free quarks and gluons. Okay. Instead, they saw something that no one had ever seen before. They saw a stuff with sort of very novel properties. They saw a fluid that existed only for a brief moment in time, but something that could best be described with hydrodynamics, with a fluid. And in particular, there's a number of interesting properties about it, but the one that I'm going to highlight is that it has a very low ratio of viscosity to entropy density. sometimes, a lot of the time, you hear people remark that it has a very low viscosity. So strictly speaking, that's a lie. The viscosity is huge compared to most other substances. But the quantity that we're really thinking about, and I'll describe a little more why this quantity, is the ratio that sort of mods out by how many degrees of freedom you have. And in terms of the viscosity over the entropy density, it was a very, very small result. So just to give a sense of the smallness, I hope I got these numbers right. Different sources mod out by 4 pi's in different places. So sorry if I messed something up here, but water, so this is eta over S. So eta, as I'll talk more next time, is the shear viscosity. So for water, I have something like 2. If it turns out I've messed up these numbers, I'll fix them when I write everything up. There's a whole bunch of different liquids, fluids that have similar values. Hydrogen and helium, when they're in fluid phases, have particularly low values of eta over S, so 0.7. So this is pretty low. And then the current sort of estimate for the quark-gluon plasma, this varies with temperature, so it's not just a single number. But I asked my colleague Paul Romachky, and he said, well, it varies with temperature. It's not a single number. I just need something to write on the board. So he said this comes in at about 0.12, maybe plus or minus 0.08. So this is not orders of magnitude, but substantially lower than for any other substance that's known. Now, when we thought that the quark-gluon plasma would be a mostly free plasma of quarks and gluons, this is something you can model with sort of perturbative QCD. But this fluid, you really can't, well, I won't say can't, but it's very difficult, because people certainly do it, it's difficult to model this using perturbative QCD. Because this fluid doesn't actually behave like a bunch of free particles. In fact, it behaves like there's no real particleness or quasi-particleness at all. It behaves like a stuff collectively for a little while, just a little while. It soon turns into a whole mess of pions, which are what you actually measure. But while this quark-gluon plasma exists, it's behaving in this sort of very unparticly way. So a hope that you might have is that maybe a gravity dual might be able to explain this sort of collective, strongly coupled behavior. And what we'll talk about next time is that not only does it explain it, at least this aspect, but you can take it as a prediction of this aspect, because calculations in ADS-CFT predicted a number very close to this several years before the quark-gluon plasma was actually observed. So that's what we'll talk about next time. Thank you. Yeah. Mm-hmm. That's a good question. I don't know the Reynolds number of the quark-gluon plasma. Does anyone know the Reynolds number of the quark-gluon plasma? I don't know.
So is it just the viscosity that tells you that it's not free particles, or is it something else?
So there are other phenomena that I won't talk about. So another well-known phenomenon that was observed is the phenomenon of jet quenching, where if heavy quarks moved through this medium, that the jet that you would expect to get from that heavy quark was considerably diminished. There are ADS-CFT ways of modeling that also, which I won't have time to get into. But so those were sort of the two big results that pointed to this behavior.
So had it been weakly coupled quasi-particles, the viscosity would have been more or less?
So if it were weakly coupled quasi-particles, I don't think people would have used the language of fluid dynamics and viscosity to describe it. Or at least that wouldn't have been as important to use. I am. All right, thanks everybody.